So now we are looking at the voltage of a 1000 microfarad capacitor and 1000 ohm resistor. The capacitor is charged right now. I can instantly discharge the capacitor by pressing the button, and this is actually the starting point for our demonstration right there, the discharge capacitor. We're going to look at the RC time constant curve to begin with. So I release the button, and there you can see we got the curve. And I'm going to try to stop so that we're at one of the divisions right at the beginning there. So I don't think I landed it perfectly, but it doesn't really matter. So due to the value of these two components, we're working with 5 volts at the power supply right there. So that's what it charges up to, 5 volts. We have the curve that you see here. So we got 1, 2, 3, 4, 5. That's about when it becomes fully charged right there, after about 5 seconds. First second, you got about 2/3 of the total difference. You can see we're up to about 3 volts right there in the first second. And then the curve, curves, and we're only about a volt and a little bit more, and then not even a volt, and so on. And after about 5 times, you consider it about leveled off. It's going to trickle charge a little bit. But in any case, that's how you look at the time constant for capacitors like this, based on the resistance and their capacitance. We're going to look at that in more detail. So that was a 1000 microfarad capacitor and a 1000 ohm resistor. So this is a 100 microfarad capacitor. So it's 1/10 the capacitance of that 1000 microfarad. This is a 10,000 ohm resistor. It's 10 times the resistance of the 1000 ohm resistor. We're going to set that there, and you're going to see it charge once I get a connection right there. And you can see a curve, of course, because capacitor, their voltage rises based on how much current is going into them. As they get a closer voltage to the supply voltage, there's less voltage across the resistor, less current, and thus it charges slower. But in any case, I'm going to press the button, and same thing. This is our starting point. We're interested in this curve for the purpose of this video right there. And make sure I hit the right button. So I'm just going to try to stop right at any division, so it's off to the right a little bit, but you can see it's basically the same curve. About 3 volts in the first second, a little less than a volt and a half it looks like in the second, and so on. You got about 2/3 of the total supply voltage, or what's left of the difference right there. So in the beginning we got the total supply voltage, it's about 2/3 of that, and then we got about 2/3 of what remains, 2/3 of what remains, and so on. And again, after 5, so in this case it's 1 second, but it doesn't have to be. You can adjust the values. Higher values will make the curve take longer, and lower value components, one or the other, it's going to go quicker. And so we lowered the capacitor by 1/10 the capacitance, and then the resistor by 10 times the resistance, so it equaled out when compared to when we used the 1000 microfarad and the 1000 ohm resistor. But we're just keeping the math easy in this video. So now we'll look at the diagram which inspired these circuits right there, other than I used 5 volts in the demonstration and I wrote 6 volts on the supply. The supply voltage doesn't matter. The 6 volts, the voltage will rise faster, but still it's going to take about 1 second with either one of these setups right here for the capacitor to charge to 2/3 of the total difference once we open the switch right there, and then a second to get about the next 2/3, and so on. And so I made it so we can see the circuit a little bit easier on there. Resistor to the positive supply, in case you had a little trouble seeing. It's coming to the top there. I could have also plugged something over here. That's one connection. That whole these 2 rows now are connected thanks to the switch, and then these bottom ones right there, they're also completely connected thanks to the switch. The switch bridges the gap, but when you press the button, all 4 corners become connected. That's how we discharge the capacitor. So yeah, we'll zoom in, and there you can see. So this assumes the switch is normally closed. That's when I'm holding it with my finger. So this is just indicating a finger press. I could have drawn the little finger to show holding it. And then when you remove the finger, that's when the capacitor will start charging. So this keeps the capacitor discharged. Got to open it to charge the capacitor. But again, we got 1,000 microfarad. So that's 1/1000th of a farad, and then 1,000 ohms right there. So they, work out to a second. You multiply them together. 1,000 times 1,000ths, 0.001 equals 1. And then the same over here. 1/10,000ths, that's what 100 microfarad means. So 0.0001 times 10,000, and so on. So yeah, I did the math right there for the 1,000 microfarad. I haven't looked at this diagram in a long time, and I also did the math for the other one right there. So I think I said it right. If I said it wrong, go by what we got there. I can see that's right. So in any case, the capacitance in farad times the resistance in ohms equals the RC time constant. That's a tau symbol, and so a tau is in seconds, and there you can see that equals the resistance times the capacitance. Again, resistance in ohms and capacitance in farads. Don't do it in microfarads. So this capacitor says 100 microfarad. You don't go by 100, you convert it to farads. So it's 10,000ths of a farad, as I mentioned before. So won't dwell on that too long. Just always be careful when you're doing the math that you got the right version. So instead of microfarads, it's farads when you do the math. And then yeah, so it's about 63%. So not quite 2/3, but really close of the difference. And again, as we saw, once in this case we had a RC time constant of 1 second. We saw that at 5 seconds it was practically fully charged. So I mean, there is like a little bit of trickle where it goes up just slightly, but it's just slightly. So you just kind of stop there at the 5th time constant when you're looking at the curve. So in any case, RC time constant's used a lot. It's used in the 555 timer, although it jumps between 2/3 of the supply voltage down to 1/3. So that change takes, about a second, not exact. Look, maybe just slightly shorter or something. But again, that change, happens pretty quickly between 2/3 and 1/3, where it gets close to 1 time constant. So not perfectly, but again, it does, a decent job. So in any case, yeah, I think that's about it. Hopefully that made sense. Thanks for watching. Make sure you check out one of the other videos I'm posting on the screen, and check out links down below. They all help out a lot. I'll see you in the next video.